Good morning. Today we are going to continue with differentiating arc hyperbolic functions, and hopefully we'll be done by the end of this class or even before that, and then we'll move on to the next section that is on parametric equations. Yeah. Okay, so we're in exercise 1.5. Let's continue to number 6. We have y is equal to ln of the hyperbolic cot inverse of x to the power of 3. So when differentiating this, you just need to keep in mind your table that involves the hyperbolic inverses and then use that. So we use the chain rule. Differentiating this using the chain rule, we start with the derivative of ln. So that is 1 over hyperbolic cot inverse. So y prime, this is 1 over hyperbolic cot inverse of x to the power of 3, and then we multiply by the derivative of what we have here in the brackets. So as you know, in the numerator we just have the derivative of this function, so x cubed. When we differentiate it, we get 3x squared, and then in the denominator we say 1 minus our function squared. This is 1 minus x cubed squared is x to the power of 6. And then we simplify this as far as possible and we'll rewrite it as a single fraction. Then we're left with 3x squared over this 1 minus x to the power of 6. Now here you have to keep in mind that x cubed, its absolute value is greater than 1. So that is the condition under which the derivative exists. Otherwise it does not. Okay, then number 8. We would do in the same way. Number 8, we have y is equal to the square root of hyperbolic cos inverse of 4x. So here again we need to make use of the chain rule. So differentiate the outside and then move to the inside. On the outside we have a square root, which is the same as power half. So the half will come down. At the top we'll have negative a half. So y prime, this is a half. The hyperbolic cos inverse of 4x, and then here we have minus a half. Then we multiply by the derivative of hyperbolic cos inverse of 4x. In the numerator we have the derivative of 4x, which is just 4, and then in the denominator we have our function squared. So say 4x squared, this is 16x squared, and then minus 1. Okay, so we can always rewrite that so that it looks better. So this is equal to 2 over the square root of hyperbolic cos inverse of 4x, 16x squared minus 1. like that. And number 10, we have y is equal to this. Okay, so we'll differentiate each of these and then add the two together. Y prime. We start with the first one, hyperbolic sine inverse of sine x. In the numerator, we have the derivative of sine x, which is cos x. And then in the denominator, we have the function squared plus 1. So sine squared plus 1, that is under a square root. Okay, so that is the derivative of this one here. And then the second one, the derivative of sine is cos. So we have cos of hyperbolic sine inverse of x. And then we multiply by the derivative of hyperbolic sine inverse, which is just 1 over the square root of x squared plus 1. Okay, so there isn't too much we can do to simplify this. I don't want to combine these two fractions as a single fraction. That would be tedious. So we can just rewrite this. X squared plus 1. So that is how our final answer will look like. And number 12, we have y is equal to hyperbolic cosec inverse of x to the power of x to the power of 3. So here, I'm sure as you know, taking logarithms would be the easiest thing to do. So doing that, we have ln of y is x cubed ln of cosec inverse of x. And then now we differentiate. On the right hand side, we will just use the product rule. So we have y prime over y. This is 2x, 3x squared ln of cosec hyperbolic inverse, and then 3x cubed times the derivative of ln, so that's 1 over cosec hyperbolic inverse of x, and then we multiply by the derivative of this one here, cosec hyperbolic inverse. Okay, and that derivative is negative 1 over x square root of x squared plus 1. Then we rewrite it so that it is as simple as possible. So we have y prime over y. This is equal to 3x squared ln of cosec hyperbolic inverse of x minus x squared over cosec hyperbolic inverse of x square root of x squared plus 1. Okay, and then we want y prime to be the subject, so we'd multiply by y on both sides. So we have y prime. This is y multiplied by 3 x squared ln sec inverse of x minus that like that. Okay, and as usual, this y you can always replace it with the definition of y in the question. It's not very long or too difficult to do. Number 14, we have parabolic cot inverse of x over y. This is ln of x plus ln of y. So differentiating this one, we start on the left-hand side. In the numerator, we should have the derivative of x over y. So to differentiate x over y, we use the quotient rule. So we get y minus x y prime over y squared. And then in the denominator, we have 1 minus the function squared. So this is just x squared over y squared. Then on the right hand side, we have 1 over x plus y prime over y. Then we want to collect all the terms with y prime together, but before that you can always simplify this fraction. So you work it out, get y minus x y prime over y squared minus x squared. Okay, and this is equal to 1 over x y prime over y. Then you want to make y prime the subject of the formula. So you collect all the terms with y prime on one side. So you can start by multiplying the denominator out. So you have y minus x y prime y squared minus x squared over x y prime y squared minus x squared over y. And then we have y prime y squared minus x squared over y plus x. This is y minus y squared minus x squared over x. And then you can divide by this bracket here on both sides. Okay. Okay, so I think that is as simple as you can leave it. I don't know if it looks that much better than what we had there, but it's always good to try and leave it as a single fraction. And the last one is number 16. Okay, and then we differentiate. We have okay, and the second part.
Good morning, Miss.
Okay, and then you can simplify this as far as possible. Yeah.
Good morning. I have a question on what's that? Why we added lean on the left side? If we added lean there, shouldn't we add another lean into the right side?
Sorry, I shouldn't have added that.
All right.
It shouldn't be there. Okay, so doing that, we have this. Okay, so that is the derivative.
Miss,
Yeah.
is the derivative of cos inverse not the square root of x squared minus 1.
Yes, this is minus. No. Like that. Okay, now it's fine. Yeah, otherwise that would be the same. Okay, so that's it on hyperbolic cos inverse functions and their derivatives. The key thing is just to use the table when you are differentiating, and then try and leave your answer in its simplest form. Then the next thing we have are the parametric functions.
Hello.
Somebody's speaking, but they're very soft.
It's number 16, man. Can you hear me?
You're very soft.
It is number 16, man. Can you please go back?
This is number 16.
Yes. Something is not adding up for me, man.
What is not adding up for you?
You use the product rule at cos and between inverse cos h and ln.
You're very soft. I don't know if you're far away from the mic or you're just speaking softly. I can barely make out what you're saying.
I am saying that the first derivative, when you first differentiated, man,
Okay.
when you're supposed to use like the product rule, I'm not seeing learn. Can you hear me, ma'am?
Yes, I can.
Yes. Learn arc sine h x. I'm not seeing it in the first derivative.
Where do you want to see it?
It should be there.
Like here? Are you still there?
The thing is, I'm trying to compare to my answer, to my steps, but something is not for adding up, man.
I don't understand what is not adding up.
Just leave, ma'am. I'll sort it out later.
Okay, so with parametric functions, the type of functions that we are differentiating, for example, you want to work out y prime, which is dy dx. But the thing with these functions is that x is a function of a third parameter. So you have x, y, and t, for example, and want to see how do we find the derivative if y is a function of x, and then x is a function of another variable. So differentiating this is not difficult because we have a formula for working out the derivative. So we have this scenario where y is equal to f of x, and then x is equal to, let me call it g of t, for example. So this is a function in terms of x, and then x is a function in terms of t, and what we want to find is dy dx. Now the formula that we use to work out this derivative is pretty simple. We have dy dx. This is equal to dy dt, or dy dt times dt dx dt. I think here we should say these are both functions of t. Okay, so here we have y is a function of t, x is also a function of t, and we want to find the derivative of y with respect to x. So the formula that we use is dy dx is equal to dy dt divided by dx dt. So if you think about this, the way we work out division, the division will change to multiplication, and then you would write the reciprocal of this, and it seems like the dt's will cancel, and then you're left with dy over dx, which is what we are trying to work out. So that's the logic behind it, not necessarily that the dt's actually cancel. Okay, and then when we want to work out the second derivative, dt y dx2, this is just d dt of dy dx, and then we divide by dx dt. Okay, so with the second derivative, you will have gotten your first derivative. You differentiate that again by dt, or you differentiate it with respect to t, and then divide by dt. So you can see here in the numerator, it's like you differentiated y twice, and here you have dt dx. The division would change to a multiplication, and then this would be a reciprocal, and it seems like the dt's will cancel, and then you'll have dx2. Okay, so that's the logic behind it. Again, not necessarily that the dt's are canceling out, but that is the logic behind it. So we can use that to work out the derivatives of some functions. Like I said, here we're given x in terms of one variable, y is in terms of that same variable, and then we want to find what is the rate of change of y with respect to x. So let's say we have x is equal to 2 sine t, and y is equal to cos squared t. Then we want to work out dy dx first. So to get dy dx, we said dy dx, this is dy dt divided by dx dt. So dy dt, differentiate this with respect to t. This is just 2 cos t times negative sine t. And then dx dt, the derivative of this is 2 cos t. Okay, then simplifying this, you can see that the 2 cos t's cancel, and then you're left with minus sine of t. That is the first derivative. Then we can work out the second derivative, say d2y dx2. We first have to differentiate dy dx in terms of t, and then divide by dx dt. So this dx dt, we already worked it out over here. So the only thing we need to work out is differentiate this with respect to t and then divide by the dx dt that we got over there. So this is equal to negative cos t divided by 2 cos t, and this is equal to negative half. So the first derivative of y with respect to x is negative sine t, and then the second derivative of y with respect to x is minus half. Okay, so here again, it is just about using the formula. So keep in mind that x and y are functions of some other variable t, and to work out the derivative of y with respect to x, that is what we have, and then this is the second derivative. Look at another one. We have x is equal to pi cos theta plus
Miss,
theta. Yeah.
let me just quickly copy the answer of the last question of the previous. Oh, thank you.
This is pi sine theta minus theta cos theta. So here you can see that x and y are both functions of theta. So to work out their derivatives, we differentiate the derivative of y with respect to x. We will just use the formula that dy dx, this is dy d theta divided by dx d theta, and then we work out each of these. So for the first one, dy d theta, this is pi minus sine theta, and then the derivative of theta sine theta, this is sine theta plus theta cos theta. Then you can put it as a fraction because I'm dividing. So dx d theta, this is pi, and then derivative of sine theta is cos theta, then the derivative of minus theta sine theta, that is minus cos theta minus theta negative sine theta, which is positive sine theta. Okay, and then if there are any terms that can cancel, you go ahead and cancel them and simplify as far as possible. So you can see minus sine theta, that's 0, cos theta, that's 0, and then the pi's will cancel. Oh, sorry guys, I'm not doing this correctly. I switched the numerator and the denominator. Should be the other way around. dy. So this is pi. Derivative of sine theta, that is cos theta, and then minus cos theta, then plus theta sine theta. So it's dy that should be in the numerator, not the derivative of that one. And then in the denominator, we have now the derivative of this one. This is minus sine theta. And then we have sine theta. And the derivative of sine theta is cos theta. Then plus theta cos theta. Okay, so I think now it's fine. Cos theta minus cos theta, theta sine theta, minus sine theta, plus sine theta, plus theta cos theta. Yes, now it's fine. Then we can cancel. This is theta sine theta over theta cos theta, which is just tan theta. And then the second derivative, dt d2y dx2. We differentiate this with respect to theta and then divide by dx d theta. So this is d theta of dy dx, and then divide by dx d theta. So that gives us the derivative of tan is sec squared of theta. Yeah.
So let's go back. Okay.
Then we have to divide by dx d theta. And dx d theta was just theta cos theta, pi cos theta d theta. Okay, so this is okay, but we know cos 1 over cos theta is sec squared is sec theta, so we have sec squared theta times sec theta, so this is sec to the power of 3 of theta over pi theta. Another one, we have y is equal to t minus parabolic cos of t, and x is equal to sine hyperbolic of t. So we want dy dx. So we say this is dy dt. So differentiate y with respect to t, and the derivative of that is 1 minus parabolic sine of t, and this is divided by the derivative of this with respect to t, which is cos hyperbolic of t. This is just 1 minus sine hyperbolic t over 50. And then we can work out the second derivative in the same way. We will differentiate this function with respect to t and then divide by the derivative of x with respect to t. So second derivative, here we have to use the quotient rule, and the quotient rule, the derivative of the numerator, which is minus hyperbolic cos, yeah.
Isn't the derivative of cos supposed to be negative sign?
We don't have cos here, we have the hyperbolic cos, which is not the same as cos.
Okay. Okay.
Okay, so the derivative of the numerator is cos hyperbolic of t, and then we multiply by the numerator as it is. So I will just have negative cos hyperbolic squared of t. And then I subtract the derivative of the denominator, which is sine hyperbolic of t, and then I multiply that by the numerator the way it is. This is 1 minus sine hyperbolic of t, and then we divide by of t. So you square the denominator. Then we still have to divide by cos hyperbolic of t, which is dx dt. So that is just the same as making this to the power of 3. Okay, so there's a lot of steps here in one, but you should be able to do that without any problems. Okay, then we can simplify. Here we just multiply out. So we'll have cos hyperbolic squared minus sine hyperbolic plus sine hyperbolic. So what we have is, yeah, yeah,
Cos h to the power of 3, mem, y, mem, but x is equal to sine h t.
I'm not dividing by x. I'm dividing by the derivative of x with respect to t.
It's 1 over sine ht, right? If you multiply,
How did you get 1 over sine ht?
by getting the, it's okay, ma'am. I see now.
Okay, so we have minus cos hyperbolic squared of t plus sine hyperbolic squared of t sine hyperbolic of t divided by cos hyperbolic of t. Okay, and then here in the numerator, that is an identity which is equal to 1. So we have 1 minus sine hyperbolic of t over cos hyperbolic of t.
Miss,
Yeah.
we do that, isn't it multiplying? Because like that, it means the one was supposed to be multiplying with sine hyperbolic of t, but then we can't
Isn't
do that, so we can't
isn't
turn
what multiplying? What is multiplying?
the sine hyperbolic squared. It's
Multiplying
multiplied
with what?
with the sine hyperbolic type of t. Okay.
Why are they multiplying?
Or like it's what's showing them is it shows that it's
Look at the
multiplied.
previous step. Look at the previous step. Were we multiplying?
No, but Miss, I'm saying what Miss wrote there.
That is a minus.
Oh, looks like a point. All
I
right.
think if you are following, you should see that it is a minus.
Ma'am,
Yeah.
in the identity, is sine sine h squared not negative in the identity?
This is -1. It is negative. This should be -1. Okay, so we move on to the exercise. (1.6) and we have number 1. We have x is equal to e to the power of 2t, and y is equal to e to the power of t sine of t. So we want to work out dy dx and also the second derivative. So dy dx, we said differentiate y with respect to t and then divide by the derivative of x with respect to t. So the first one, this is e the t sine t plus e to the t cos t. And then we divide by the derivative of e to the power of 2t. So divided by or multiply by 1 over 2 e to the power of 2t. So here we can see that e to the power of t is a common factor, so we can take it out. So e to the t sine t cos t over 2 e to the 2t. Okay, and then this just leaves us with sine t plus cos t over 2 e to the power of t. Then we want to work out the second derivative. The second derivative, we have to differentiate this with respect to t and then divide by dx dt. So dy dx2. So this one, we're going to differentiate it. So the derivative is the denominator as it is multiplied by the derivative of the numerator. So we have 2e to the t, then the derivative of the numerator, this is cos t minus sine t, and then the numerator as it is multiplied by the denominator's derivative. So this is this 2 minus e to the power of t, and then the numerator is sine t plus cos t, close the brackets, then this is all over the denominator squared. Okay, then in the numerator, you can factor out the e to the power, the 2e to the power of t, and cancel whatever can cancel. So this is 2e to the power of t. Then you're left with cos t minus sine t plus sine t minus cos t over 4e to the power of 2t. So the cos t's will cancel. Here we're getting 0. Did I do this correctly? Let me just check. I'll go back and see. That's different from what I have here.
The sine t is negative. The second sine t is negative.
The second sine t is negative. Yes, that's why. Okay. So this would be negative. So the 2's will also cancel. The e to the power of t will cancel. Then I have e to the power of t there. So I have negative 2 sine t over 2 e to the power of t, and the 2's here will cancel. It's negative sine t over e to the power of t. That is still different from what I have here. Okay, so we say the numerator as it is, sorry, denominator as it is, multiplied by the derivative of the numerator, so that is cos minus sine, then the derivative of the denominator and the numerator as it is, sine t cos t, and then you square the denominator. Okay, that looks fine. Then we still need to divide by, the derivative of x with respect to t. So here, don't even have any space. Okay, so what's missing? We need to divide by dx dt. Dx dt is this one here. So divide by 2 e to the power of 2t, or multiply by 1 over 2 e to the power of 2t. Okay, so this whole thing has to be multiplied by 1 over 2 e to the power of 2t. And then we multiply by 1 over 2 e to the power of 2t. Okay. Negative sine t over 2 e to the power of 3t. I don't know if that is correct now. Okay, let's see what I did wrong. This should be a minus. Okay, so you can check this one again. Maybe doing too many steps all at once is not a good idea, or definitely it is not. So very easy to make a mistake and forget something. But just go over this one in case there's something that I missed, because the answer I have here is different than the one I'm getting there, but it looks like you did it correctly. Do the rest of the exercises, or the rest of the questions in exercise 1.6. Then on Monday, we should finish off with this chapter and start with the applications of derivatives. Okay.
Ma'am,
Yeah.